Hello? Hi, Angela. Can you
Hi.
hear me?
Yeah, I can hear you.
Okay, thank you very much. Hello, everyone. My name is Matthew Toe, so the technical lead of TRONZ. TRONZ is a community developers in Tron, and our mission is to provide better security and better privacy to all of our users. As the first big thing that we are going to bring you in Tron 4.0, we are really excited to tell you that we are bringing you the shielded transaction and also shielded contract into our Tron ecosystem. So let me share the slide first. Okay, can everyone see my slide right now? Okay, good. So today I'm going to introduce the zero knowledge proof inside our Tron virtual machine. And to kickstart, let's introduce zero knowledge proof itself. I'm sure that a lot of you had heard of the term zero knowledge proof a lot of times, but what exactly it is? So it is an idea to prove something to a verifier without telling anything about it at all. So, for example, I have $1 million and want to prove to a verifier. Then the verifier would ask me, hey, show me your $1 million, please. But instead of showing her the money, I would have another method to prove that I actually own the $1 million, just doesn't show it to her. So there are three properties of the zero knowledge proof. The first one, if the statement is true, then the honest verifier will be convinced by the fact that he is an honest prover. Second, if the statement is false, then no cheating prover can convince the honest verifier that it is true. And finally, if the statement is true, then no verifier learns anything about the statement except the statement is true. So that is the fundamental of the zero knowledge proof. And among the decades, there are numerous research has been proposed. And right now, there are three major zero knowledge proof very popular inside our blockchain industry, and we are going to compare them one by one. They are bulletproof, CK Starks, and CK Snarks. So if we look at different aspects of these three zero knowledge proof, it is not hard for us to find the best solution among them. In terms of the proof size, the CK Snarks perform the best with only 196 bytes. Bulletproof takes around 6 times more, and CK Starks takes around 200 times more. And in terms of the verification time, again, zero snarks perform the best. And bulletproof, the verification time is about 1.1 seconds, which is really, really poor performance. And the same goes to proof of time as well. Well, while there are some compromises of the proof of time and also CK snarks need a trusted setup, but we can conclude that the CK snark is the best to use among the three of them. And that's why we chose it as our implementation. So the CK snark scheme involves a bunch of cryptographic procedures, but I'm not going to talk through them one by one, but basically the idea is that it turns a statement, something like, I know the key that allow me to spend a shielded transaction, and turns it into a quadratic arithmetic program. And it is a quadratic equation like what we've learned back in high school, and whoever knows the solution of this program would actually have the right to spend the shielded transaction. Now, moving on to our shielded transaction protocol. So the shielded account system is quite different from our ordinary account, and it has a series of keys. But don't worry, the only thing you need to know is that all the keys are derived from one spending key at the top, and also all the other keys serve different purpose throughout the process. And on the other hand, the protocol is based on an unspent transaction output model, which is UTXO model in short. And whenever a user spends a node, it needs to generate a spend description. And the same goes to when somebody wants to receive the money, they have to generate the receipt description as well. And both of these description will act as an input and output of every transaction. And every transaction links one after and one by one. And that forms the UTXO model. Now, when our protocol is defined, moving on to create our own shielded contract. Well, to do that, we have to provide the functionality of hiding the source address, destination address, and also the transaction amount of our TRC20 token. And to do that, we've implemented in TIP135 with 3 core functions: mint, transfer, and burn. Well, maybe you could already guess what the 3 functions are doing based on this name. So the mint function is to transform a public TRC20 token into a shielded token. So therefore, it has 1 transparent input and 1 shielded output. Second, the transfer function is to transfer the shielded token to somebody else, which it could hide the source address, destination address, and also the transaction amount. And you could put up to 2 transactions inside a transfer function. And therefore, you could have up to 2 shielded input and also 2 shielded output. Finally, the burn function, which is to transform the shielded token back into the public TRC20 token. And therefore, it has 1 shielded output, 1 shielded input, 1 transparent output. And by different scenarios, it might also have 0 or 1 shielded output as well. Well, maybe you could have a clearer idea by looking at this flow diagram. So, for example, if Alice wants to transfer the TRC20 token, just for example, to her friend Bob secretly, then she will first have to mint the token into a shielded TRC20 token. And after several steps of transfer, it will then finally burn the token and then convert it back into a public TRC20 just token. And then the whole process finished. Bob can secretly receive the money from Alice. Now, having our created shielded TRC20 contract, as it is same as the smart contract deployment, everyone can deploy a smart contract. And therefore, we have to also implement some instructions in order to verify the shielded contract. And in TIP137 and 138, we've implemented 4 new instructions for the verification process, which are the verify mint proof, verify transfer proof, and also the verify burn proof. One more is the Patterson hash. So as you could tell it from the name, the verify proof instructions are used to verify the validity of the functions that we have just mentioned inside our shielded contract. And all of this takes around 10 milliseconds. And for the Patterson hash instruction, it's used to compute the node value inside the Merkle tree. And therefore, it returns the parent node value inside the Merkle tree as well. So the time cost only takes around 1 millisecond. So our performance is pretty quick. Well, having everything set up, there's one more thing we need to build is the trusted setup. And therefore, we initiated the multi-party computation torch project. And it was officially launched by Justin Sun, the founder of TRONZ himself, back in January this year. And as you can see, Justin himself did actually participated inside the torch project. And in honor of the pioneer work of every participant, we do giving them $100 to every one of them. And finally, there are a total of 196 participants, including developers from the TRONZ community, blockchain enthusiasts, daily active users, and KOLs, which are key opinion leaders. And it is the most participated MPC project by numbers around our blockchain industry. So it is quite of a success. Well, to wrap things up, let's compare our shielded TRC20 contract and transaction with the other projects in the blockchain industry. First of all, Monero, one of the very first projects which provides privacy in blockchain, it uses ring city protocol, but its size is linear with the ring size And also, it uses a bulletproof, which, as we've just mentioned before, it has a very poor performance. So the other one, the Zcash, it uses ZK stacks, same as us, and it also provides perfect privacy, but it doesn't provide the support of the shielded contract, which means that there's nothing you could do if you want to extend the privacy. Grin, another popular project, uses the Mimble-Wimble protocol. It could hide the transaction amount, but again, it uses bulletproof, which offers poor performance, and it requires the sender and receiver to have some interactions before they do the transaction, so it's not convenient. Tornado Cash, a very popular project in Ethereum, it supports shielded contract, but it only supports deposit and withdrawal. And you could only deposit a dedicated amount to someone else. So let's say if you want to send 2 ETH to somebody else, you have to do twice. So one ETH twice. And also it uses a mixed solution, which means that its privacy is proportional to the number of active users. And there is no point of bringing you any privacy at all if there's only one single user using this method. AC tag. Now, it is shielded amount, but they generate an address, public address, even though it is one time off, but it is public to both sender and receiver. When you compare to all of the above projects, our shielded TRC20 contract could offer you great performance, low transaction fee, perfect privacy, and is convenient to use, and most importantly, it is extendable with smart contract. So I guess that's the end of the zero-knowledge proof in our TRON virtual machine. And let's move on to the final part. What is our vision? Well, TRONs are devoted to the research of frontier cryptographic techniques, and we want to make a contribution to the privacy protection inside the blockchain industry. And if there are any more new methods to be proposed in the future which provides better privacy or better performance, we would try our best to bring that into our TRON ecosystem. But right now, there are so much more that we would like to do. And we can't wait to see that happens. And thank you for all of you listening. I hope that our shielded contract and shielded transaction would bring TRON 4.0 to a whole new level. Thank you.